I'm David Lenrow, currently the CEO and founder of a very small company that nobody's ever heard of, and we're not talking about what we're doing yet. Previously, my last couple jobs, I worked in software-defined networking and open source software development at Huawei most recently and at Hewlett-Packard. Prior to that, I was on the technical steering committees of the OPNFV project, an open source NFV project, and the Open Daylight project, which was an open source SDN controller. I was the chairman of Northbound Interface and the Open Networking Foundation, where we did a lot of work on intent from kind of about 2013 through 16, and currently chair for intent-based orchestration in the MEF forum and working on starting up a intent project in that venue. And the title of the talk is based on the fact that traditionally we've had dumb infrastructure and you have to treat it like it's dumb. We're now starting to have smart infrastructure and understand, the reasons why we want to build smart infrastructure. And it's time to stop treating the network or the cloud infrastructure like it's dumb. So I'll talk a little bit about evolution and change, talk about intent concepts and what defines an intent-based system. I think I'm actually going to skip over the NFV example, but then there's a couple examples of how you might add encryption to an application using a network and sort of the trade-offs of doing it at the top of the stack versus the bottom of the stack. Similar kind of discussion for adding multipath routing, and talk some more about the impact of deploying in infrastructure. So this is kind of a variation on the old joke often credited to, I forget who it's credited to, but the idea is you're in Manhattan somewhere and you see a musician getting out of a taxi cab and you ask him, how do I get to Carnegie Hall? And he answers, practice, practice, practice. In our case, the way you get to Carnegie Hall physically has changed a lot over the years. There was a time when if I said, go to Carnegie Hall, well, they hadn't really developed Manhattan yet, but if you were Henry Hudson, you'd sail your boat and move the tiller around and move the sails around until you got there. Fortunately, we have advanced a little bit beyond that, and then there was a time when you'd get out your tourist book and your maps and get all confused and look for landmarks. And finally, we've evolved to the point where you punch in the address or the name of the place into your navigation app, and it tells you how to get there. And so we've done a great job of evolving with technology and capability, and we've made it much, much easier for people to get where they're going. In networking, we haven't. And in infrastructure, in general, we haven't. I find it's funny whenever I ask my mom, for the address for someplace, she insists on giving me street-by-street instructions, and I just have to kind of grit my teeth and hold my breath and wait till she gets to the address so I can punch it into my nav system, because that's going to get me there a lot better than remembering everything my mom told me. So we're trying to get there. In networking today, it's pretty much you get in your boat and you move the sails around and you sort of hope you get there. If you wanted to tell someone how to get to Carnegie Hall in that analogy, you'd be talking about sailing things and navigation things, not, clicking on your smartphone. On the network, it's pretty much the same thing. Create this interface with this protocol and assign this address to this thing. Intent-based networking is really about the idea that we describe what we're trying to do, not how to do it. It's about the how and not the what. And make sure I didn't skip a slide. So for several years in the ONF, we talked about this, and we actually put together a pretty decent document that tried to describe in sort of technical detail what makes something an intent-based system and what doesn't. And unfortunately, while we were working on that, lots of other people were building similar things and had different ideas about what intent-based means. And it was a little frustrating that, we weren't sure this would become kind of authoritative in any particular way. Recently, everybody and their brother has decided that intent-based is good, and so there's been a lot of confusion. And more recently, oh, don't tell me that slide disappeared. One of the analysts has provided definition of what is an intent-based system. And it really starts out, and the first principle is really you describe what you need, not how to do it. And then there's some other elements of that which have to do with automatically translating the what into the how, and then finally building the system as sort of an infinite loop, which is perpetually looking at the state of everything in the system and the what you asked for, and potentially making changes to the how in order to continue to fulfill. So if you said, Bob and Fred need to be able to communicate, and that's your basic concept, and it's got you running over some set of routers and switches, and one of them fails, the system can go back and reroute that, send it through a different way, and still fulfilling your original intent, which was communication between these two endpoints. And so if you say what we're really trying to do is get the how separated from the what, that becomes the methodology for designing this scheme. You look at any particular thing that's an attribute of delivering the service, and you say, if it's part of the implementation, it goes in one bucket, and if it's part of what you're trying to do rather than the implementation, it goes in another bucket. And so that's really the, how do you decide if it's intent or not? You examine it and you ask, is there anything in here that's implementation specific that's going to have to change? And so the intent should never change. You know, you're trying to go to the airport. That never changes. Whether you take a taxi or you get on a bus or you have someone drive you, that can all change. And so we're trying to build a similar kind of an interface. And in particular, in technology and in networking user interfaces, CLI, typically there's some high-level concepts of what you're trying to do and lots of low-level concepts of how you're going to do it. And they're all mixed together in such a way that anybody that wants to use the system has to be an expert in both things. It's similar to if you had you needed to bring an auto mechanic with you anytime you drove your car in the back seat in case you had to deal with some aspect of repairing the car. That's, again, kind of where we are in networking today. And so the idea was to create a world that's much simpler than that for one set of users. Instead of everybody that wants to run an application on the network has to be an expert in network infrastructure, we said, wouldn't it be nice if there was a simplified virtual world where you didn't have to worry about all those details and you could just talk about what you want? And that's really the intent world. We got a lot of pushback in the early days, and people said you're oversimplifying. You're trying to make all this complicated stuff go away. This is zero sum. It can't go away. This intent thing's crazy. It'll never work. So we finally were able to kind of turn that conversation around and say nothing is going away. All of the complexity is there. All of the detailed prescription is there. We're just splitting it into two different categories of stuff. And so, you know, when you go through that kind of analysis, you find that most of the things that you use to talk to network solutions today are not intent because they're not portable and they're not persistent across different conditions. Anything that refers to a device or a device type or a vendor, a protocol, header bits, where in the world it is or where in the network it is, none of that is intent. That's not what you're trying to accomplish. Those are probably things that are getting in the way of what you're trying to accomplish. And the intent is much more abstracted. It's, you know, here's a bunch of things that all have the same behavior, and here's the behavior that they should have. Bob and Fred and Joe are in the sales group, and people in the sales group are allowed to connect to the secret server. You can state all of those kinds of things without ever understanding anything about networking, and we want to design that kind of an interface for applications and business people so that they can get their stuff done on the network. Some small number of people still have to be experts and help the system translate the intent into the implementation through what we call mappings. And you know, the idea here is really to find this narrow waist that we're always looking for in API design, where there's a kind of single place where everybody can refer to the same thing in the same way. Above it, you can have all kinds of amazing diversity of solutions. Below it, you can have all kinds of amazing diversity of you know, equipment and platforms, but we're trying to really get to a common interface that allows you to change things above or below that demarc without changing the results and the behavior. And so one of the things that's nice about this is we expose a much smaller attack surface. The idea was that we were going to have these SDN controllers, and they were going to have all these sophisticated modules that did special stuff inside of them, and we were going to expose the APIs to this to everybody, and they could do whatever they wanted with it. It's pretty easy to see if you start letting people make changes to your topology or your inventory in a way that isn't consistent with reality, the system's broken and it can't function correctly. In the case of the intent-based API, the only thing we expose is the here's what I need. There's no way you can modify packets or change the inventory or change the database because you're not even allowed to touch it. You're not even allowed to look at it. You're not even allowed to know it exists. All you're allowed to do is say, here's what I need. The system either says, okay, I'm going to do that forever until you tell me not to, or it throws a fault and says, sorry, I can't do that for you right now. And part of what's good about this is if you over-prescribe or you overly micromanage what you want for a solution, how you want it to work, you're probably not doing it in a way that's very well optimized because you're only thinking about what you're trying to do. And so, in this example, if you ask the Tylenol delivery man for an aspirin, you're not going to get anything. You're going to go away with a headache. If you tell the Tylenol delivery man, I have a headache, do you have anything that can help me? He says, here's a Tylenol. And so you don't want to tell the system too much about how to do it because you eliminate degrees of freedom that allow the system to be optimized and balanced. And furthermore, this scales arbitrarily. The intent when you're on an edge domain is the same as the intent when you're in the transit domain, or you're in a cloud provider domain, or you're in your customer's domain. Bob and Fred can communicate. That's the intent. That never changes. It doesn't care where you are in the world. And as a result, you can implement it locally in each of these administrative domains in a way that makes sense within that domain and doesn't require you to know anything about how anybody does anything in a different domain. And kind of the ultimate goal of this is really this kind of a self-service portal. All the concepts in here are things that you understand as a business person without having to be a networking expert. And you can use this kind of a system to describe, here's a bunch of servers that are related in some way because they're part of the sales organization. Here's this thing called the internet, which is the Wild West, and dangerous things happen out there. And when traffic goes from one to the other, I want it to be audited, and I want to use encryption, et cetera, et cetera. And even though 300 megabits per second is quantitative and it's numerical, which sounds like the how-to, not the what-to, in fact, that is also intent. 300 megabits per second is true whether you're doing it on optical or copper, whether you're doing it with MPLS or VXLAN, it doesn't make any difference. So this is still implementation dependent, and it can be quantitative and specific and still be implementation independent. And so one of the things we've learned along the way, and this is really kind of getting to the heart of how do we get real-time and interactive application support into the system as a whole. The original vision of software-defined networking was that kind of the interface was going to be this low-level interface, basically a forwarding table interface. And we decided that the whole world is a forwarding table, and if we have a nice analogy, we have a nice abstraction for it called OpenFlow, we're done. But in that world, the way you end up making the applications is, again, the forwarding table is dumb. It doesn't know how to do anything. So if you want to do something intelligent on top of it, you're going to have to basically figure out the state of the entire OpenFlow network, figure out the relationships between all the nodes, build all the flow rules, track all the network state and topology, update things in real time. And so in this example on the left, we're doing that for a particular kind of unified communications application. It has to do all that stuff. It makes the application much bigger, much more complicated. You need a much more diverse team of developers to develop it. There's more to maintain. And when you're done, there's probably an application next to you doing, say, streaming media, which functionally is almost identical to what you're doing in your UCC application. But because we've decided that the application was the right place to do it, you end up with another set of the exact same logic done differently. It's not interoperable, it's not compatible, it has different bugs, it's huge and complicated, and you've had to hire this huge team of people, and you can replicate that. Maybe there's 1,000 applications with very similar behavior, and 1,000 of them need to have a do-it-yourself SDN controller built into them so that they can manage this dumb thing at the bottom, which is just a flow table, forwarding table kind of a thing. On the right, you see how the advantages of building this into the infrastructure. So on the left-hand side, you've got really thick application, really thin controller. On the right-hand side, we've inverted that. We've generalized the things that real-time interactive media applications need into some set of media logic, and we put it into the controller. Then all of that other stuff, the flow rules and the topology and the inventory, we build that once and exactly once inside the controller. Everybody else uses it, gets the benefit of it. There's no incompatibilities. You don't have to fix bugs in 27 different places. And at the end of the day, if you want to write an application that uses those features, it's a very small application, and the team of people that build it don't have to understand OpenFlow and SDN controllers and all the rest of it. So that's kind of the general theme, is there's just a bunch of advantages to extending the platform to provide this as a service rather than pushing the burden all the way out to everybody who's using the system. And so, continuing that theme, kind of a layering 101, why you do things at the bottom of the stack if you can avoid doing them at the top of the stack. We want to look at, again, encrypting payload for a networked application. You could put all of that logic into the application. You could recognize that the operating system has some encryption stuff built into it. Or you could make encrypted payload an attribute of the network interface and never worry about it. And we'll look in more detail how that works, and then kind of a similar where should we put it and why for a different use case. So this is kind of the put it all in the application. It's great in the sense that you don't have to worry about what are the OS dependencies, do I have the right stuff in my kernel or not. Doesn't matter, it all comes with the application. If you got the application, you can do it. The traffic comes out of the application encrypted, and off you go. Easy. But again, you've got this problem of building tons of profound stuff way up high in the stack and having to maintain complete state for a system that you don't own and you don't have anything to do with. The next sort of approach to doing this is to recognize, well, the operating system has crypto libraries and has some public key infrastructure, so I don't actually have to invent all of that stuff. I can be smarter and make my application more efficient and take advantage of that service that's already built into the operating system. Having said that, in almost every mainstream operating system, the current crypto engine in the current distribution is obsolete. Even if it's not entirely obsolete, the version that you're running probably has tons of known vulnerabilities and needs to be patched. And again, you can replicate that for every single endpoint and every single user of the system. Finally, you could make encrypted an attribute of the system. The only change you need to make in the application is to have the application tell the system these flows need the encryption attribute. There's no new code to make the application more complicated. There's no operating system dependencies whatsoever. A single entity that runs this encrypted cloud can be responsible for getting the latest crypto engine in the universe, making sure it's completely up to date and patched, and that every single user of the system is using the same version of that software. So clearly the better alternative is to build things higher or build things lower in the stack wherever possible, and it fits into this model of you tell it once what it is you need, you put it into a closed-loop feedback system that spends all of its time making sure that that state exists regardless of other changes of state in the entire system, and you use a simple API to tell the system what it is you're trying to do rather than getting into manipulating packets and forwarding tables and working at that state. And we'll get into just what a huge problem it is harvesting state out of a complex system when we talk about the next use case. And so, the way to think about this is really all the stuff that interactive multimedia applications need from the network can be described by the things that are in a typical SLA. latency, jitter, bandwidth, things of that nature. And so rather than getting into describing a whole bunch of things that are unique to the use case, we recognize that essentially if the interface to the system is to provide kind of an SLA level description of what you need, you can then forget about the how do we make that come true and enable the system to do it in the most efficient way. And we invest once in putting the understanding of how to deliver this behavior into the controller, into the infrastructure itself, and everybody gets the benefit of it through kind of a black box, kind of an API. So I'm going to fly through these because I think we're running a little behind. But this was an example of a universal communications application that wants to take advantage of multipath network connectivity. And the way you do it currently with a sort of a dumb controller is you extract the entire network state out of the controller in order to figure out which links are being utilized the most and how do I piece together a path that has the best opportunity to do that. And realistically, that's probably changing at kind of a microsecond granularity. So not only do you need to harvest this massive state and start trying to analyze it, but you also need to somehow keep up with the changes of state. I mean, all of this is going to go on inside the controller. This is what the controller does. It spends its life monitoring the state of the system and doing things about it. To try and export all that data to a different system that has a subset of it and doesn't have the same intelligence and make better decisions is crazy. And then in addition, you get the replication problem. Not only are you going to have one application trying to harvest huge amounts of stuff and make state changes in the system, but you're going to have other applications trying to do the same thing. They're ships in the night. They step all over each other. One makes changes that break the other. Just doesn't work. If you make sort of smart multipath usage or some similar kind of concept part of the system, you build all that same stuff, but you build it once inside the system where you've got real-time, up-to-date state available to you all the time. You've already got tons of logic that's paying attention to the topology and the inventory and the match action state in all your devices. You don't have to even know there are devices. You just have to express this path needs this special behavior. Call me when you're done. End of story. So that's really a quick fly-through on just the current architecture battle that's going on. Lots of people are trying to build this stuff up in the application layer. And, as a person who cares a lot about architecture, that's kind of my thing. It just makes me crazy. It's clear that that's the wrong way to do it for a whole bunch of reasons that I've just described. And we're hoping to work in the MEF, among other organizations, to kind of build some real-world proof points that we can enable these features in a way that's completely non-intrusive and minimizes change to the applications. Thank you. I don't know if we have time for a question or two. Or questions, anyone? Yes. Small closed systems, I guess, right? I mean, the propagation is the hard part of this. Conceptually, I haven't said anything subtle. I doubt there's a word I said that wasn't kind of obvious as soon as I said it to people that are systems thinkers. But how do you get the best effort internet dumb core with smart applications all around it? How do you migrate that? It's kind of a boil the ocean problem. And so I think the way it's going to happen is people will have localized success doing this, write the white papers and the case studies that show that we were able to, make our network engineers more efficient and, have them spend time on strategic projects and save this much CapEx and this much OpEx. And then we'll see some investment, maybe from the provider side to building these features into kind of public infrastructure. But I think, we've got to see people succeed with this on a small scale, and then we've got to kind of sell it to the people that have impact on the larger scale. And MEF seems like the right place to do it for now, and that's why we're starting those efforts. Thank you.
Thank you very much.